We are back, everybody, talking about reciprocal functions again. Alright, now in the last video we covered, well, part of the first goal anyway, and we talked about a little bit of the second goal. You now know how to identify the asymptotes of the graph of a reciprocal function. We haven't put it into practice yet, but we're going to do that in this video. And then we're also going to put into practice the second goal, in which you're going to sketch and analyze the graph of a reciprocal function. Now here's all the stuff that we discussed in the last video about what a reciprocal function is, where the asymptotes are, what the graph is called, the symmetries involved, all that kind of stuff. Alright, so now let's go ahead and take a look at the equation of a rational function, reciprocal function, more correctly here, and let's go ahead and sketch this graph, write down its asymptotes, all that kind of stuff. The graph of y equals negative 4 over x. Now, the fact that we have a k that's negative tells you that we're going to have this kind of graph right here. Correct? We said this is what you get whenever k is negative for a reciprocal function. And you already know where the asymptotes are going to be as well. In fact, when you start graphing a reciprocal function, I'd like you to start by always knowing where the asymptotes are. Alright. Well, the vertical asymptote is going to be x equals 0, and the horizontal asymptote is going to be y equals 0. Let's go ahead and write that down as the directions tell us. And then simply what I would like us to do in order to continue making the rest of the graph is to go ahead and make a table of values. And we're going to put 6 points into our table of values. Alright, create that chart, please. Now what makes the most sense to me in terms of input values is this. Our function divides negative 4 by a number. Why don't we pick some numbers that negative 4 is pretty easily divisible by? And I'd like us to pick 3 negative numbers so that we can get this half of the graph, and 3 positive numbers so that we can get this half of the graph. Remember, you cannot plug in 0. That's the only option that you absolutely do not have here. Well, 4 is easily divisible by 1, 2, 4, 8, 16, those kinds of things. So let's do this. Let's plug in negative 4, negative 2, negative 1, and then positive 1, positive 2, and positive 4. And go ahead and get our output values. If we plug in negative 4 divided by negative 4 is 1. Negative 4 divided by negative 2 is 2. Negative 4 divided by negative 1 is going to be 4. So that's going to give us the first branch. The different sections of this graph are called branches. That's going to give us the first branch of the graph of this reciprocal function. And then the second one is going to be given by the positive x values. Negative 4 divided by 1 is negative 4. Negative 4 divided by 2 is negative 2. Negative 4 divided by 4 is negative 1. Those are the points that you're going to graph. Go ahead and plot those values, and if you know how to make the curve based on what I showed you in the last video, do it. If not, you can wait on me to catch up. Quick note, I realized I pointed out the wrong branch a moment ago. Whenever we're dealing with a negative value of k, that was what was in orange, wasn't it? And so that was this and this. It was a branch in the second quadrant and the fourth quadrant. And you can tell from the points that you graphed right here that that's what's going to happen here as well. Now, as soon as you've got your points graphed and you're ready to make the branch, remember what you need to do is make it so that the asymptotes are boundaries for your graph. So your graph will approach those boundaries, but it will not quite touch those boundaries. So start it off, I typically will draw from left to right, really close to the x-axis. Whoops, that's not the thickness I want. Start it off really close to the x-axis, and then just curve it up, and then use the y-axis as a boundary as well. Get really close, but never quite get there. Alright, do the same thing with the other branch. We're going to start it off, if we're going from left to right, really close to the y-axis, and then curve it through those 3 points. That's making the graph of a reciprocal function. Pretty darn simple, isn't it? Okay, now we can obviously throw in some translations, some dilations, and that kind of thing, which we're going to throw in a translation right now, as a matter of fact. Let's check out the next example. And I want to see if you can tell me already, based on our previous conversations in the other video, what effect this plus 10 is going to have. We're going to sketch a graph of y equals 200 over x, big number, no matter. Sketch a graph of y equals 200 over x plus 10. We're going to write down its asymptotes as well. Well, alright, remember the asymptotes were based on what you could not use for an input and what you could not possibly get for an output. you still can't divide by 0, can you? So your vertical asymptote is still going to be the line x equals 0. For our horizontal asymptote, though, remember that it's impossible to get 0 when you divide 200 or any positive number by something. Impossible to get 0. And if it's impossible for 200 divided by x to be 0, it's impossible for 200 over x plus 10 to ever be equal to 10. So basically this value, our vertical translation out there, corresponds directly with where our horizontal asymptote is going to be. It's going to be the line y equals 10. And since that line is not the x-axis, we're going to graph it momentarily. But before we graph, I would like to have an idea with these really large numbers what our intervals are going to be on each axis. And so let's go ahead and make our table of values so we can talk about that and get something that's pretty reasonable. And as I spoke of with the previous video, we'd like to pick some values that are easily divisible by our value of k. And so that number is 200. We could easily divide that by, 5s, 10s, 20s, 40s, 50s, those kinds of things. And we'd like to divide by 3 negative numbers to get this half of the graph and 3 positive numbers to get that half of the graph. So I'm going to say that I'm going to go with negative 50, negative 40, and negative 10. Alright, and then I'll just go with the opposites of those things as well. Many other choices ahead, but those were pretty good for us. And then let's go ahead and take turns dividing 200 by each of those numbers, and remember to add 10 to the end. If I plug in negative 50, I'll have negative 40 plus 10, which is negative 30. And so forth. Go ahead and find the rest of the y coordinates real quick. Pause the video and do that, please. Alright, my mistake. Don't like making these division mistakes right there. 200 divided by negative 50 is negative 4, isn't it? And then negative 4 plus 10 is 6. So that's what we ought to have right there instead of that negative 30. My mistake. 200 divided by negative 40 is negative 5. Plus 10 is 5. 200 divided by negative 10 is negative 20. Negative 20 plus 10. Am I getting that right? I feel like I'm missing that for some reason. No, that's right. Negative 20 plus 10 is going to give you negative 5, or negative 10, excuse me. Okay, and then it turns out you get the opposite. Oh no, you won't get the opposites of those values. 200 divided by 10 is 20. 20 plus 10 is 30. 200 divided by 40 is 50, plus 10 is 60. And then 200 divided by 50 is 4. No, I missed the last one again. Wow, you would think division would be a little bit easier, wouldn't you? Alright, 200 divided by 40 is 5, plus 10 is 15. And then 200 divided by 50 is 4. 4 plus 10 is 14. Those are the points that we want to graph. Now I want to pay attention to the size of the numbers that we're using right here. Doesn't it make sense to you for the intervals that we are choosing to go by tens? Probably on both axes, going by tens is pretty good. We might get away with going by 5s actually on the y-axis. I think I'll do that, but tens for sure on the x-axis. Remember to label your intervals if they're not going by 1s, as I've done right there, so it's very easy to identify them. And before we actually graph the points, which we'll do pretty shortly, let's graph that horizontal asymptote, that line y equals 10. And so remember that the asymptotes act as boundaries, so after you graph all these ordered pairs, you're going to use this line along with the y-axis for your boundaries for the two branches that you make. See what you can do with that. Alright, and so that will look like this for the branch on the left half of the graph. Whoops. And, oh, we're on the next graph already, didn't mean to be. It'll look like this for the graph on the branch on the right hand side of the y-axis. Very simple to make these graphs, right? Okay, now we need to tackle a problem that's going to be a word problem, and it's going to involve us to use and analyze the graph of a reciprocal function, rather. All right, so let's take a look at that. You're going to want to copy this information down. It says that the acceleration a, and this means in meters per second squared. Instead of writing in meters per second squared like that, it is often written as meters per second squared this way, but you need to get used to this notation. All right. The acceleration of a in meters per second squared for an object of mass m kilograms to exert a force of 2,000 newtons is given by the function a equals 2,000 divided by m. Okay, so you can calculate the acceleration that would give you a force of 2,000 newtons based on the mass of an object that would be providing that force. What we're going to do first is we're going to sketch that graph with these limitations, these restrictions, so to speak. We're going to say that the mass, we're going to graph it for objects that have a mass between 0 and 200 kilograms, and we're going to look at for when the acceleration is between 0 and 10 meters per second squared. So let's go ahead and choose the appropriate intervals. First of all, you're going to notice that I only have the first quadrant graphed because we're only considering positive masses. You can't really have a negative mass. In a sense, you can have a negative acceleration, but that implies direction. For the purposes of this problem, we won't have any negative accelerations nor negative masses. Let's choose our intervals then that we're going to use. And I would suggest going by tens on the horizontal axis potentially. Tell you what, I'm going to go by 20s. The tens won't quite get me to 200 by the time that I'm over to this part right here. Ones will be more than sufficient to get me up to 10 on the vertical axis. Okay, so the fact that we're only dealing with positive values for m means we're only going to get one branch for our reciprocal function. And we need to know where is going to be the vertical and the horizontal asymptote of this branch. And since there's no translations involved, that means the x-axis, or the m-axis in this case, and the vertical axis are going to be our asymptotes again. And so we need to just make a table of values where we can plug in some different values of m and figure out the corresponding values of a that go along with them. M is our input, A is our output. And remember, we're only doing half the graph, so 3 points will be more than sufficient. Think of some things that are easily divisible by 2,000. And also, we're trying to keep the acceleration below 10, so we want to make these pretty large numbers. Let's say we divide by 200, or plug in rather, 200 kilograms, 400 kilograms, and 500 kilograms. Wow, that wouldn't make a lot of sense, would it? All right, we need to change our restrictions a little bit. I just noticed we're going to get numbers that were too big for A. So let's say we're going up to 50 for A, which means we need to change these intervals. Instead of going by 2s, I think going by 5s will be fine there. And I still want to plug in numbers within my domain into the function. So 200 is the largest I can plug in. Let's pick some other numbers that 2,000 is easily divisible by. Let's say 150 can be the other two numbers that we plug in. All right, that makes more sense in the context of this problem. Okay, 2,000, and when I plug in 200, 2,000 divided by 200 is going to be 10. 2,000 divided by 100 is going to be 20. And 2,000 divided by 50 is going to be 40. So let's go ahead and sketch the graph. Now, one interesting thing to consider while we're actually making this graph is that we do want to only show the portion that's between 0 and 200 kilograms. So we're actually going to stop the graph right here at this point rather than continue past it like you normally would. All right, so the branch will look like this then. And we'll stop there. Okay, so there's the graph of our function that tells you the acceleration of the object needed for a given mass to apply a force of 2,000 newtons. All right, let's take a look at the next parts of this problem. The next thing that we're asked is, what is the acceleration of the object applying the force if its mass is 100 kilograms? Now remember, the object is going to apply a force of 2,000 newtons. That's just the parameter for the problem. So, mass is 100 kilograms, what would the acceleration have to be? There's a couple of ways that we can go about that. One of those is that we can just simply use our function and we can plug in 100 for m, right? And we can say then that A would be equal to 2,000 divided by 100, And that would be 20, and then you want to give the units. The units for acceleration here were meters per second squared. The other thing that you can do is you can use the graph. Now this will be maybe less accurate since we did it by hand than it could be otherwise, but watch what I'm doing. I could find 100 on the mass axis, the horizontal axis, and I can draw a horizontal line up until that hits our curve, and then I can find out what y coordinate or a coordinate belongs with that by going over to the vertical axis, and that corresponds with 20, doesn't it? So two ways of getting the same thing. Go ahead and find out what the acceleration would be if the force is caused by a 60 kilogram object. Now by plugging in 60 in place of m in your function, you get 2,000 divided by 60, which is about 33.3 if you round it to three significant figures. 33.3 meters per second squared. And you would have gotten a similar number, probably not quite so accurate, if you had used the graph like this. Here is 60. And draw a line up. Whoops, I want to use this. Draw a line up to where that intersects our curve. Draw a line over. See what the y coordinate is. See, there's 20. There's 30. And so we would have said about 38 using my graph right there. It wasn't perfectly accurate, was it? But still a pretty good estimate nonetheless. If IB gave you the graph, you could trust this method in order to figure out what that acceleration would have been. Alright, one more example to go along with this, or one more part to this question I mean to say. And it's kind of going backwards from what we just did. Now it's asking what is the mass required to apply the force for an object that can accelerate at 8 meters per second squared. Tell you what, I'm going to change that. Instead of 8, let's say 15 meters per second squared. Because the other way, the mass was not going to be less than 200 kilograms. Alright, well, two ways of doing this. One of them is using the equation again, and this is the more accurate way of doing it. You're going to get a more precise answer. Instead of saying, we know the function is acceleration equals 2,000 divided by m. So you could solve for m if you plug in 15 for a. And then you just have to divide or multiply both sides by m. And then divide by the acceleration. And to three significant figures, you're going to get about 133 kilograms. We again could have used our graph to come up with that estimate there, just simply by going up to 15 on the acceleration axis, drawing a line across, and then drawing a line down to your horizontal axis to see what mass corresponds with it. And then we're counting down by 20s here, aren't we? So that's 200, 180, 160, about 140 is what I would have gotten with my graph that way. Alright, that's how you graph a reciprocal function and how you analyze the graph as well. Thanks for watching. You're good for 5.2.